Hello, good morning, everyone. I'm Leah with Headwaters Science Institute. Welcome to another exciting edition of Lunch with a Scientist, where you will get to meet one of Truckey's own wonderful scientists who's out in the world doing amazing things, Justin Ondry. And I'm going to introduce him in just a minute. Before we get to that, just a quick reminder that our summer programs are up and live, and they start June 21st. I just wanted to let everyone know that we've extended our financial aid deadline until March 31st. So you've got an opportunity to apply for financial assistance. All are welcome to apply. You can find the application on our website for both our general research experience and our girls summer research program, which are really good opportunities for high school students to learn how to do hands-on research. So if you're interested, please visit our website. Feel free to apply for financial assistance or grab a regular registration spot. And we really look forward to working with you this summer. So with that said, I'm very excited to tell you all about Justin. He grew up in Truckee, California, near where Headwaters is based, and he graduated from Truckee High School in 2011. He has a PhD in physical chemistry, which he received in 2020 from the University of California, Berkeley. And while he was there, he used transmission electron microscopy to study the structure and defects in semiconductor nanocrystals. And if that sounds like a mouthful, you're going to learn more about what he does today. So in his talk, he's going to discuss how scientists are able to look at individual atoms using an electron microscope and learn how this has enabled breakthrough discoveries in physical and biological sciences. So, super excited to welcome Justin Ondry. Hi, Justin.
Everyone.
So the secret here is you're actually not in Truckee or in Berkeley. Where are you today?
I'm in Chicago, actually, where I'm a postdoctoral researcher at the University of Chicago.
Fantastic. And can you tell us what you're working on there?
Yeah, so here I'm working on trying to make new materials for electronics applications. So think, for example, something in your screen that you're viewing this on is creating the colors that you're seeing. And I'm trying to make new materials that can make better colors, brighter colors, more pure colors for next generation displays. That's just one example of an application of the things that I work on.
Really neat. Something that can be felt in households across the nation. That's awesome. Well, Justin, we're really excited to hear more. So I'm going to let you launch into your presentation.
Yeah. So one of the things that everything around us is made out of atoms, put together in various different ways. And something that's really important for scientists is to be able to understand how the atoms are arranged, to understand, what gives a material its certain properties, or why does a material behave in a certain way. And so I'm going to tell you about how we actually are able to look at these atoms directly. So before we begin, I want to give you an idea of how small atoms actually are. So if I was giving this talk to you in person, you'd see that I'm about 2 meters tall. So you can kind of conceptualize how big that is. But what I want to do is I want to compare that to how much smaller atoms are compared to me. And typically, atoms in a material are about 2 angstroms apart from each other. I don't know if you've ever heard of this unit, but this is 2 times 10 to the minus 10 meters. Or if we're used to inches, 0.0000. Anyway, you get the point. It's really, really small. And so, for example, we may have heard of the material diamond. Each of the carbon atoms in diamond are 1.5 angstroms apart from each other. So I hope that gives you a little bit of perspective of how hard of a problem it is if we wanted to even see these little tiny atoms that are so close to each other. So one way I like to try to emphasize this is let's think about things that are bigger to the same order of magnitude as atoms are smaller compared to me. So that would equate to 20 billion meters, or 2 times 10 to the 10 meters, or 12 million some odd miles. And so some numbers that equates to are 1/7 the distance between the Earth and the Sun, or about 500 times around the circumference of the Earth. So think about how small I am, or any of us are, compared to these distances. And that's how small atoms are compared to ourselves. So to this day, I've been working in this kind of field for quite a while now, and I still don't fully grasp how small these things are. And it's kind of amazing, the differences in scale that we work in. So now what I want to ask this question is, could we see these atoms with a light microscope? Some of you may have in a biology class, or with Headwaters, maybe you would see a typical light microscope like this. And we can see things like little microbes swimming around in water with a light microscope like this. What if we just made a really, really nice one? Would we be able to see atoms? And before we ask that question, we need to define something here. And this is the idea of resolution. So when I say something is not resolved, imagine you're looking at a car really far away. You know that the headlights are creating two distinct beams of light. But if you're too far away, you can't see that it's two distinct points. It's only one. And that's what I'm showing right here on the left. Whereas if that car gets closer, you can eventually see that that's actually two distinct bright light sources. And so a light microscope, this is the only equation I'm going to show you. The resolution of the microscope depends on this numeric constant times the wavelength of light that you use, divided by what we call the numerical aperture, which is just a constant. So that constant is typically 1. And if we plug in these numbers where we use a typical wavelength of light, which is about 500 nanometers, we get out that the resolution of a typical light microscope is only going to be able to achieve about 300 nanometer resolution. So we'd have to, the closest some things could be such that we could see that they're two distinct things rather than one big blob, is they have to be at least 300 nanometers apart. So that's pretty far. And this technology of a light microscope was actually more or less perfected in the 1890s. A microscope that one had available back then is no better or worse than what we can make today. And so all of that comes down to the fact that light behaves like a wave. Some of you may have been exposed to this in a physics or chemistry class, but basically all the different colors of light that we see are just different wavelengths of that light. And one of the key features of light is that when it goes through a small slit like this, you actually create what's called an interference pattern. So you don't get just the result where you get a bright spot only where that slit is, but the waves interfere with each other and create kind of this oscillation pattern. And that result, or the fact that light behaves like that, is how scientists derive an equation like this that tells us what the limiting ultimate resolution we could achieve with a light microscope is. And I'm going to show you this. Typically, when I give this talk in person, I can use my laser pointer and actually demonstrate this to you directly. Unfortunately, you're just going to have to take photos as my proof of this. But I take this laser pointer and I shine it on what we call a diffraction grating, which is essentially a bunch of little slits. And what we see is that it doesn't just reflect like a mirror. You see all of these different bright beams come out. And that's because the light's undergoing what we call diffraction. I can project it onto the wall of my apartment, and you can see these several distinct spots. And the fact that light behaves like a wave is what prevents us from resolving things that are too close together. So now some of us may have come into contact with this idea of electrons. So electrons are these elementary particles that make up our the atoms, and you can do all kinds of things with electrons, like make a beam of them and potentially use them to image things. And a very long time ago now, some scientists determined that electrons also behave like waves. It's kind of hard to see here, but what they're showing here is a plot of like the intensity of electrons versus position. And you can see this oscillation, which is very similar to what I've shown you here. And so you may think, well, if they behave like waves, we're going to have the same problems that we have with light, and we may not be able to look at things that are really close together. But it turns out that the wavelength of these electrons depends on their energy. Again, I don't need you to know the details of this equation, but they figured all of this out. And the important thing is that the wavelength of electrons is very different than the wavelength of light. So I showed you this before, where if we use this equation, we can see that the wavelength of light really is proportional to the resolution that you can get out. But if I told you for electrons, which we know behave like waves, they're bound by this same equation in the ultimate limit. But the only difference is, and that's what these scientists discovered, is that the wavelength of electrons is much, much smaller than the wavelength of light, on the order of 0.003 nanometers. So if we go ahead and plug those different numbers into this equation, what comes out is that the theoretical resolution of a microscope that used electrons as the imaging medium rather than light is 0.015 angstroms. So I'm going to remind you again that a typical atomic spacing is on the order of 2 angstroms. So I'll ask you a rhetorical question of whether light, or whether these electrons could potentially be used to image individual atoms. And the answer is yes. Yes, it is theoretically possible. So with these ideas in mind, in the 1930s, scientists started experimenting with trying to build an electron microscope, kind of building off of the ideas of optical microscopes. And so in 1931 was the first demonstration of this. And despite all of the potential of these electron microscopes potentially being way better than light microscopes, this first iteration of the electron microscope was way worse than a light microscope. This is often the case with science, where to take steps forward, we sometimes have to go back in our abilities, but we know that there's a really good potential in this train of thought, and so we keep working on it. And so I'm not going to go through any of the technical sides of what it took to get to the potential to see atoms, but over 70 years of technical innovation, these modern transmission electron microscopes can see atoms. And typically we can achieve 0.5 angstrom resolution. And so I want to just take a moment to talk about how sensitive these microscopes are. This is the microscope. The company places it inside this box that isolates it from vibrations in the room and temperature fluctuations and noise, because all of those little tiny movements can make it impossible to see the atoms, even if the microscope was able to. And then the scientists who are operating that microscope are actually in a different room, and that's because all humans create a little bit of heat, and the heat that we create would cause enough instabilities for this microscope that it would not be able to work as well as it theoretically could. So I think it's just really cool to see like how far something like this has been able to go. And on the inside, these microscopes are just filled with sensitive electronics and wires. I think there's like, someone did the math, it's like 3 or 4 households worth of wiring is in one of these microscopes. And this is what it takes to be able to see atoms. And I'll get to that now, of what we can actually do with this. And I'm going to show you a bunch of really cool results. These aren't things that I've done, but these are things that I think really emphasize and are great examples of what these systems are capable of. And only at the end I'll circle back to what I've done with them. So some of us may have heard of this material called graphene, which is a single layer of carbon atoms with this kind of honeycomb lattice. And this honeycomb lattice makes it this material that's exceptionally strong, way stronger than even steel on a mass basis. And part of that comes down to the way this hexagonal arrangement of atoms. And scientists are now able to use one of these electron microscopes, and each one of these bright dots here is a single carbon atom, and you can see the hexagon lattice that results. And this is a scale bar showing that this is 5 angstroms, and so this is around 2 angstroms between each of these atoms. So we can actually see these atoms, which I think is just amazing. And then up in the upper part of this image is actually where there's 2 layers of carbon atoms stacked on top of each other. And these brighter dots are where there's actually 2 atoms right on top of each other. And so you can see now, we can understand the structure of not only a single layer, but 2 layers. I just think this is so cool that we can see this. And the ability to see this has enabled us to understand why graphene works in this way and why it's so strong. And that enables us, with that understanding, to identify other materials that may be even better than graphene. So now what I'm going to do is, this is all in 2 dimensions. You're seeing a 2-dimensional image of a single layer of carbon. But the world around us is in 3 dimensions. All the materials everything is 3 dimensions for the most part. And so we want to be able to understand the atoms in 3 dimensions. And what scientists can do is we can do what's called tomography. So if you imagine you have an object and you take a bunch of images of it in different orientations, you can use a computer to put those images back together and understand now the 3-dimensional structure. And so some scientists are able to do that. In this case, they've taken a tiny little crystal of iron and platinum, and they were able to identify in 3 dimensions where every single iron and platinum atom is, and how they're distributed within the material. And they were able to identify these different domains within the nanocrystal, and from that we can infer the properties. So these materials are really important for making components in a computer such that you can store information. And so understanding the structure of this enables scientists to make better hard drives that can store more data, which is, again, an ever-increasing part of our lives. So I'm a material scientist by training, and that's what I mostly focus on, is looking at materials. But the biology side of this is also incredibly powerful. So I'm going to just show a few examples here. The first one is the ribosome. So you've seen in your textbooks, probably in biology, like, this is a ribosome. It looks kind of like this. And that's the part of the cell that converts RNA into proteins. It's very critical. And so to understand the structure of it and how it works, you have to know what the structure is. And so structural biologists use these electron microscopes, and they take tons of pictures of something like the ribosome, and they use computers to put those images together and generate these three-dimensional structures of, for example, the ribosome. In this case, it was really cool because it was a ribosome with a protein, an RNA inside of it, so that they can really understand not only kind of on a larger scale, but how all of the atoms in this ribosome are arranged. So these are key insights that help biologists understand how the cell works on a molecular level. And then I'm going to show you, last but not least, a very recent example of how these electron microscopes have, I think, starting to impact all of our lives today. We've all seen in some form this rendering of the SARS-CoV-2 virus. So that's what causes COVID-19, the virus that has made many people sick, and many people have died and have closed schools, all of these things. And just now we're starting to get vaccines for that. And I'm going to show you how electron microscopy actually played a pretty key role in doing that. So we've all seen this rendering. Where did that come from? How did scientists come up with this? And actually, it turns out all of this is based on electron microscopy characterization of viruses. So in early January of 2020, so this is about a month after the initial reports of, wow, there's this new virus going around, scientists had taken an image where there's this blob here with these little spikes coming off of it. And this is where these things called coronaviruses get their name. They have these spikes around this corona of around the virus, or around this central part of the virus. And so this helped them identify, okay, well, this is the class of thing we're dealing with. And that provided, companies with information of like, well, how do we start making a vaccine for a coronavirus? And then not much later, in March of 2020, some groups published the atomic resolution structure of one of these spike proteins. So this spike protein was, my understanding, is the key to how this virus gets into your cell. And if you can understand how that spike protein works and understand ways to mimic it without making you sick, that's the key to making an effective vaccine. And so these structures that were published and generated by electron microscopy were instrumental in the eventual effort to develop a vaccine for this virus. And so it really blows my mind that this, from discovery of a new virus in late 2019 to only a few months later, we know the atomic resolution structure of the outer part of it is that I think really shows the power of these electron microscopes and how they can really impact everyone. So what do I do with an electron microscope? This is what I'm going to end with. I don't do anything nearly as cool as what these groups of scientists have done. But what I do is I make these nanocrystals that emit light. So this is a picture I took from my fume hood where I mix together different chemicals such that they react and grow little tiny pieces of crystal of some material such that they emit light. And by changing the size and composition of these materials, we can make them emit light anywhere from blue to red light. You can imagine how this is potentially really useful for a display because you need to make all of the colors. And really one of the big targets of this is how do we make a display as efficient as possible, such that you use the least amount of electricity to generate bright, efficient light coming out. Because whether we like it or not, TVs are getting bigger and they actually use a lot of electricity. So if we can make it so that they use less, that'll have really big impacts on our global footprint. So this is a picture of me during my PhD in front of the electron microscope that I was using. Right here on this screen is actually, you're not seeing the electron beam, but what you're seeing is the electron beam hits something that creates visible light so that we can then see where the electron beam is and see images that it generates. And then what I mostly use it for is to look at defects in these little crystals. So this is an image I took of some nanocrystals that have a defect in the middle. So all of these atoms are kind of arranged in rows and columns, just like, corn in a cornfield or something like that. And whenever there's a place where the order is messed up, that makes the material less good at emitting light, for example. And we want to understand how to get rid of these defects. So we can use the electron microscope to take images of these defects, and then, there it goes. I can take videos of these defects being expelled from the crystal. So you saw, hopefully, maybe we can play it again, and maybe not. We saw how this crystal spontaneously became much more uniform. You see all the ducks are in a row, I'd like to say. And from that insight, it tells us how can we make these nanocrystals better and brighter. So with that, I really thank you for taking the time to listen to me and hear about what I do. And I'd love to take any questions that you may have.
Great. Thank you so much, Justin. I think it's fascinating that you, like I said earlier, work on this technology that can be maybe felt in homes all across the country someday. Speaking of homes and what people are doing at home relating to your research, I wanted to ask you, I think that microscope technology has come pretty far, and a lot of people who have kids may have a little fun microscope that they can kind of look through. And I'm sure that that is vastly different from an electron microscope. And so are you looking in it and receiving an actual image, or does it come out as a printout? And can you tell us more about how it's operated?
Yeah, so there are many different ways you can get the information out. In some cases, you see the image directly projected on the screen. So you saw that glowing green bit. You can see, if you operate in a certain way, you can actually see the image directly on that fluorescent screen. But typically we'll use a camera that's somewhat, in some ways, similar to a camera you'd use on a normal light microscope, but modified such that it can see electrons, essentially, rather than light. And so typically we work with these as digital images, and we do all the processing on the computer. So we could print it out if we wanted to, but it's typically easier to work with digital data.
And can you explain to us what the substance is like that you would be looking at? Is it the substance in its original form, or is it derived somehow into a solution, or what does that look like?
So there's many different ways. So the materials that I work with are kind of a solid that you can dissolve into a solvent. So when I work with it, it's dissolved in a vial, and you can pour it and all of that. But then when I want to look at it in the microscope, I put it on a little support that's really, really thin that electrons can go through. And then I put a little small droplet of my material on it, and the solvent evaporates, just like water would evaporate from something, leaving behind the little solid nanocrystals kind of arranged on this substrate, and I can go around and look at different ones and stuff.
Neat. So it's similar to how we at home are looking at leaves under our microscopes, but a lot more advanced.
Yeah, it is very similar. And I think one thing, I remember when I was a kid, I had a little microscope that I played with. And I always struggled I wanted to look at a raisin once. And I put it on the little microscope slide like they said, but I couldn't see through it. And that's because the raisin was way too thick. The light never went through the whole raisin. And it's a similar problem that we run into with these microscopes, is that we have to make the samples in a very specific way such that we can even have a chance of seeing through them.
Mm-hmm.
So yeah, a lot of the concepts that get from light microscopy apply here as well.
Yeah. So it's such a cool technological advance that we have these electron microscopes now. Are they becoming more prevalent, or do they still exist in just a few labs? Where can you find them?
Pretty much, so they are very prevalent in academic and industrial research labs. They're commercial instruments, and basically any research or most teaching universities will have at least one of some capacity that students use for experiments and also for research. So they're very available, but outside of kind of academic research and industry, there's very little accessibility. They're quite expensive, unfortunately.
I see. And who's building them? It sounds like quite an involved process to put one together.
Yeah, so there's like 3 or 4 companies that manufacture them, and so they manufacture. They have 70. Some of them have 70 years of experience building these. So every 3 to 5 years, just like an iPhone, they're refining the technology in that way. And so so researchers themselves don't typically build these microscopes. We just use them and purchase them from a manufacturer.
So it sounds like you can use one in a lot of different disciplines of research, and you gave us a few different examples. Can you dig a little bit more into maybe some of the future research that you might do using an electron microscope?
Yeah. So as I had mentioned, kind of now I'm working on making new materials for light emission. So these are materials potentially that no one's ever made before. And so the most important thing when you make a new thing in chemistry especially, it's not just enough to say that you made it. You have to prove to people beyond reasonable doubt that you made it. And these microscopes provide, in addition to the ability to see where the atoms are, they can tell us what the atoms are. So it can tell me, for example, if this sample is made of, 2 different elements or 3 different elements, and potentially where those elements are. So that's another thing that I'll be using this for. It's mostly as a tool for characterization to know.
Interesting. And how is that information received? Does that come as a printout, or is that something that's an equation that you then have to interpret?
Typically, it's in the form of a printout of data. Typically in like a text file, or a lot of times, unfortunately, it comes out in a form that can be only read by the software that the manufacturer gives you to operate this detector on the instrument. So that can be hard sometimes, but yeah.
Fascinating. So what you do is so neat. It's at like the intersection of technology and science, and working with very, very infinitely tiny materials. How did you get into this field of research? Were you always curious, and how did you get here?
Yeah, so when I was in high school, I really enjoyed chemistry classes and the physics classes. I just thought that was always really exciting. We would do things and things would change colors, and I was like, wow, trying to understand that. So then, that really started at UCLA. In my undergrad, I started out, I think, as a geology major because I was like, rocks are cool. But then I took an introductory chemistry class that I had to take for that major. And actually, the professor showed me some of those quantum dots that glowed different colors. And I was like, wow, this is so cool. Like, how does this work? So then I kind of continued down that path. I learned chemistry very well. And then one thing led to another. And now I did my PhD mostly looking at the atoms in materials. So I guess the point I want to get across is that just because you have ideas in your mind of like chemistry being something where you're just mixing stuff together in beakers, that's not true at all. We do all kinds of things spanning from building and thinking about fancy instruments like this to making molecules, to probing how bacteria work, it really spans dimensions. So if you're interested in that, like, it's a great place to start.
Mm-hmm. And I'm interested. Off the screen, you told us that you were interested in going into becoming a teacher. And I wonder what your thoughts are with that path and why you've decided to pursue education.
Yeah, so I really like, for me, it's really fun to see when, if I understand how something works, watching when you're teaching someone how to do a new experiment, or and that light bulb goes off in their head where they're like, oh my gosh, this makes sense, like the world makes sense. That's really cool to see. And science is a place where that happens a lot, and I want to pass that kind of passion on to other people.
That's great. So we're going to wrap up in a sec here, Justin, but I have a couple fun questions for you.
Okay.
First off, what's your favorite part of the research that you do?
Oh, that's a good question. I think one of my favorite parts is an unfortunate reality of doing research, at least especially doing synthetic research like I do. Most of the things that you try don't work the first time or the 10th time, unfortunately. But when it does work, when you've worked on something for long enough where all the pieces start clicking in, things start working, you're like, wow, I created a kind of a new unit of knowledge that no one else had before. And even though that unit of knowledge may be very small, it's still very rewarding because it's something that all of humanity didn't know before. So for me, that's really rewarding.
And what's the coolest thing you've ever seen under a microscope?
I'm
sure there's
that
lots.
I've taken the image of, or that someone else has?
I would say that you have.
So I didn't show this here, but one of the things that I did for a while is I made these little nanocrystals such that they all had a regular shape. So they all were hexagon shaped. And so just like when you tile a floor, right, you put together a bunch of shapes and they make something that makes a nice smooth surface that's really well ordered. We can do that at the nanoscale as well. We can make these tiny little tiles that are shaped like hexagons or squares, and they'll randomly assemble into these perfect little lattices, just like you'd see when you look at a tile floor or a cobblestone street. And just by controlling the shape and the size of these nanocrystals, that spontaneously happens at the nanoscale. So I've taken a lot of images of those, and it's really fun.
Fascinating. It's incredible that we see patterns everywhere in our modern world, and at the cellular and molecular level as well. Neat. So I want to leave off on some inspiration for the students who are watching. If one of them is interested in pursuing some kind of career similar to yours, what educational path or life path would you recommend for them?
Yeah, I mean, definitely, if you're in high school right now, kind of the key is really trying to understand why you're learning the things you're learning, and why they work, not just how they work, but why. And after that, really you can't go wrong if you go to a university. There's opportunities to get involved in research, kind of no matter where you go, whether you take a pathway of going to a community college and transferring to a four-year school, or going directly to a four-year college. There's ways to get involved in research in all of those, so you really can't go wrong. The path I took, I went directly to UCLA, which is a large research university, and so I had opportunities kind of where I got to work in research labs with the professors who I was taking classes from. But if that's not your style, you don't want to go to a large school, that's totally fine. There's plenty of small schools, smaller colleges where you can pursue research opportunities in the summer. So I guess what I'm saying is there's no one path. The path that I took is one path, but everyone's unique, and there's many ways to get involved in this, I guess.
That's great. Thank you so much for sharing, Justin Ondry. Always nice to have one of our own from the Truckee area proof that you can be born and raised in a tiny town and go on to do huge things. So we really appreciate you being here.
Oh, of course, anytime.
Thank you very much.